will be done then after the 2 sections. And then, towards the end in week 13, we'll look at whatever we didn't cover on this paper and maybe some other questions from another paper. All right, so I'll just give a minute or two for people to sign in. And I'll put the slides up on, I was going to say Solace, on Brightspace afterwards. So they'll be there for you afterwards. So don't feel that you've got to try and take everything down. But the best thing to try and do is to see, look, could you think of how would you go about doing the questions as I'm kind of going through them? I won't stop to give you, time to do all the questions or anything like that, but it would be a good idea to just be thinking, okay, well, how would I go about it? And have an A4 pad and a pen next to you and try doing them, because, it just makes the class more interesting for yourself. And then at the end of the session, you can be all right, okay, well, what do I need to revise, or how much of that do I think I'd be able to do? So it kind of just gives you a better idea of where you are. All right, so we'll get started. Now, just when we're kind of starting, sometimes there's people that can be waiting in the lobby. All right, sorry about that. Just sometimes there could be people trying to sign in, so I just left them in. And so that might happen a bit at the start, all right, just where people are trying to get in. All right, so you should be able to see the screen there now, and I'm just going to go through the starting question. So the exam has 2 sections, probability and stats, and you have to do 2 questions from each, so 4 in total. All right, and all the questions carry the same. Now, this part is important, right? Where is it? All of your work must be shown clearly and logically using appropriate symbols and notation. Now, and it does say, like failure to do so will lose marks. So the probability notation is important, and, appropriate symbols, and it is written there. So, like if you don't do it, because it's written there, it's kind of, someone could come back to you afterwards and say, well, look, it's written there. So you have to try and write down all the notation as properly as you can. And as well, a good idea would be write down the formula that you're going to use at each stage before filling it in with numbers. That's just, if you make a mistake, then, you'd end up getting most of the marks if they can see what it is that you were going to do. Okay. All right, so the first one, we're given the probability of A is 0.35, the probability of B is 0.6, and the probability of A union B is 0.9. And then they're asking us to find some probabilities there. All right, so A is 0.35, B is 0.6, and A union B is 0.9. So the first thing I'd be doing there is to draw a Venn diagram and see if you could fill into it. And I could just hear some more people coming in, so I'm just going to set it up, and I'm going to ask you try and fill into that while I just let the people into the room again. So the probability of A, we're told that that's 0.35. So suppose here's A, and then let's say here's B. Okay, and the probability of B is 0.6. Now we know that the union, the total probability has to be 1. And they did tell us that the probability of A union B is 0.9. So we've been given this information as well, the probability of A union B. So that's everything just in A and B. All right, so but we have the total law of probability for part 1 would tell us that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So could you try see if you can fill in that Venn diagram? Now, so for the probability of A, we should be getting 0.35 inside the probability of A circle. And suppose I just make the probability of B be the red circle. Inside that red circle, we should have 0.6. Inside the black, we should have 0.35. So the first thing to do is to try and figure out what goes into the intersection, because then you can kind of figure out how to fill that in. And I'm just going to let some more people in. Okay. So we were told, that A union B is 0.9. So that's everything in the black and red circle has to come to 0.9. So that means there's only 0.1 left over. So I'll put 0.1 out here anyway. Okay, so the total probability has to add to give me 1. Now we need to figure out what goes into the intersection, because once I figure out what goes into the intersection, we can fill in the rest of it. Okay, and we have this, the law of total probability, and that would be given to you in the tables as well. Now, I think I have them on the last slide, right? So these probabilities, these formulas would be given to you. All right, so as well, I would open up the back pages of the exam. You could rip off the back pages and have all the formulas there. There's a lot of formulas given. All right, and I would do that before starting the exam, and then you don't have to keep flicking back through them. So the probability of A union B, they told us, was 0.9. The probability of A, we know, is 0.35. The probability of B, 0.6. And what we're looking for is the probability of A intersect B. Now again, do you see the way, as they said it in the instructions, right? We wrote down the formula we're going to use, and now we're filling it in numbers. So even if you do make a small mistake or something, if I was correcting this, I'd say, okay, they picked the right formula. They're trying to figure out what the A intersect B is. They're doing the right things. All right, so you'd be picking up marks. So then just rearranging that, we'd get that the probability of A intersect B is equal to 0.9, but I suppose minus 0.9 plus 0.35 plus 0.6. All right, and so we end up getting there probability of A, I'll mute that person in a second now, but probability of A intersect B, it gives us 0.05. All right, so what we have in here then is 0.05. Well, what we're supposed to have in probability of A altogether in that black circle is 0.35. We already have 0.05, so now we just need another 0.3. And then in B, in the red circle, we're supposed to have 0.6. We already have 0.05, so we're left with 0.55. And now you'll see that what's in the red and black gives us the 0.9, which is the union of A and B. And part 1 actually was find the probability of A intersect B. So we already have A intersect B done. And part 2 is asking us to find the probability of A given that B has happened, so the conditional probability. Now the formula again that we'd use there, so the probability of A given that B has happened is the probability of A intersect B all over the probability of B. So that's conditional formula, conditional probability. There's our formula we're going to use, and now you should be able to use that to figure out what is the probability of A given that B has happened. And there was somebody trying to come in there again. So I just... All right. So filling in there then, we're going to get that the probability of A, given that B has happened, is the probability of A intersect B. Well, we figured that out from the first part, so it's 0.05, and the probability of B we were given in the question is 0.6. Okay, so that's approximately equal to 0.083 that works out to give us. All right, so 0.05 divided by 0.6 works out to be around about 0.083. All right, and in the last part of that asks you find the probability of A complement intersect B. Right, so the probability of A complement intersect B. All right, so that's what we're looking for now. Okay, well, we just looked at conditional probability. You know, a while ago I said that the probability of A, given that B has happened, is equal to the probability of A intersect B all over the probability of B. So if I was to look for, let's say, the probability of A intersect B, well, then rearranging this formula, multiplying both sides by the probability of B, we'd get that that's equal to the probability of A given B by the probability of B. And then you'd know this as, let's say, well, the next part that's coming as Bayes' theorem. So if we were to think about what we've been asked for now, right, we're looking for the probability of A complement intersect B. Okay, so that's what we're looking for. So I could think, well, look, the probability of A complement, given that B has happened, is equal to the probability of A complement intersect B all over the probability of B. So then we'd have that the probability of A complement intersect B could be written as the probability of A complement given that B has happened times the probability of B. Okay, but I mean, I could have written that another way as well. You know, we could say as well that, you know, the probability of B given A complement is the probability of B intersect A complement all over the probability of A complement. Still just using the formula that we have up here, just using other versions of that. So that means that I could also write, you know what I could write over here using these two results. Okay, we could say that the probability of A complement intersect B could be written as the probability of A complement given that B has happened by the probability of B, or it could be written as, if we were to rearrange, you know, if I was to rearrange this to get the probability of B intersect A complement on its own, it would be the probability of B given that A complement has happened by the probability of A complement. So now I could say that, you know, we can find the probability of A complement intersect B by either getting the probability of A complement given that B has happened by the probability of B, or by getting the probability of B given A complement times the probability of A complement. Or, I mean, you could say, why are you doing all this anyway? We could just look at the diagram and figure it out from there. Yeah, you could. Okay, but I'm just trying to write down, you know, the appropriate notation and symbols. But of course you could look at it from a diagram point of view as well. So suppose if we say that now the probability of A complement intersect B is equal to, there's a couple of ways you can go about looking at it. Let's look at it. We'll say the probability of B given that A complement has happened. Let's look at this one. The probability of B given that A complement has happened times the probability of A complement. So if you look at your Venn diagram again and look at, okay, where is A complement? And I'm just going to maybe leave a little bit of room to finish that here. We'll just draw the diagram. So if we have, there's A, and I think I had B in red. Okay, well then, what is A complement? A complement is everything except A. So this would be there's A complement. So then if they said, okay, what's the probability of B happening given that you know A complement has happened? Okay, so there's my B. So I mean, what we're looking for then is A complement has happened. So the black shaded region has occurred. What is the probability, given that we know that that has occurred already, what's the probability that B happens? So, well, really we're only looking for then this bit. What's the probability? Let's say you could think about it as throwing a dart. If I know that the dart landed somewhere in A complement, what are the chances that it's in that part of B that's also in A complement? So what are the chances it's in that blue part? Well, if we go back and look, what is the probability of A complement? A complement now is all the black shaded region. So it's everything except what's in A. Okay, and what's in A is 0.35. So the probability of A complement happening, right? The probability that A complement happens is, and just looking back there, everything but not A. Well, if you look at A is 0.35, so everything else is 0.65, right? So we get the probability of A complement is 0.65. What's the probability then of it being in just that blue part of B? Well, we go back to our diagram that we already drew. That's only 0.55. So we've got a 0.55 chance out of 0.65. So you'd be saying it's 0.55 all over 0.65, because that's the probability of B given that A complement has happened, times the probability of A complement. Well, the probability of A complement again is 0.65. So then we end up just getting 0.55 is the probability of A complement intersect B. Now, I mean, to be fair, you might say there was, there honestly wasn't any need to write it in such a way, but I probably would, just in case that you'd make a mistake, because let's say you could have just drawn, what is A complement intersect B? Well, if you look at it, here's B. This is, I mean, if you were to just think about it in diagram form, right, there's B. That's the probability of B happening. And the probability of A complement happening was all of the black shaded region. So what's the probability of A complement intersect B? The two of them happening at the same time. Well, the only thing they have in common there is that blue part of B, which is the 0.55. So you could have done it by looking at the diagram. You could have also done it by, like I compared this part to this. You could have gone for the probability of A complement intersect B is equal to the probability of A complement given that B has happened by the probability of B as well. Okay, so you had a couple of options for doing that one, but I wrote down one of them there. All right, so that's part A. And then moving on to part B, it says, consider the probability. Now, I'll check in with questions after I've done the first part of B. Maybe I'll check in if there's any questions in the chat. I won't see the chat while I'm actually doing the questions, but I'll keep a look in as we're going through. And just feel free to interrupt with the microphone if you want. Anytime, just ask a question. Don't be thinking, oh God, I can't now. She's in the middle of a question. Just stop. Just stop me and ask. All right. Or else type it into the chat. So consider the probability density function f of x equal to 2e to the minus x, where x is between 0 and b. And what they're asking you for is what's the value of b? Okay, well, part one, for a valid probability density function, all right, we have that the integral from a to b of f of x dx is equal to 1. So just like the total probability in the Venn diagram was 1, well, if we have a probability density function where x is any, any random variable between 0 and b, well, then it's going to be that the integral from a to b of f of x dx must give me 1. The total probability, again, must give me 1. That is for a valid probability density function. All right, and so then they wanted to know what is the value of b. So we have the integral from 0 to b of f of x, which is 2e to the minus x dx, should give me 1. All right, so if you integrate e to the minus x, we get minus e to the minus x. So that's going to give me minus 2e to the minus x, evaluated from 0 to b, should give me 1. So just filling in your upper limit and subtract, fill in your lower limit, should give me 1. Now e to the 0 is just 1, so that's 2. Okay, and then we get 1 minus 2 is minus 1. And so we have that e to the minus b then is a half. And remember, we're trying to find what b is. So let's take the natural log of both sides. So we'd have the natural log of e to the minus b is equal to the natural log of a half. And so then we get minus b times the natural log of e is equal to the natural log of a half. And so then we have that minus b is the natural log of a half. Now I can write that then as the natural log of, well, 1 over 2 to the 1. I can write that as 2 to the minus 1. That if you have, let's say, x to the minus m, that's the same as saying 1 all over x to the positive m, right? That's from rules of indices. And then I have that minus b then is equal to minus the natural log of 2. And that's from, if you have, a times the natural log of b, that's the same as saying the natural log of b all raised to the power of a. That's one of your rules of logs. All right, so we get that minus b is minus the ln of 2, so then b is the natural log of 2. And I'd probably just leave it like that. Instead of getting it as a decimal, I'd probably just leave it because we might need to use it again. All right, so that's part one. So the big thing there again is, well, for a valid probability density function, the integral there from a to b must give you 1. And so that was the formula that we used. And then we filled into our formula. Calculate the probability then that x is less than 0.3. Okay, so I mean, we're talking about some function. Let's say we have some function and we're talking from going from 0 to b, where, if you like, the total area underneath that curve would have to be equal to 1. Now, we just figured out that that's the ln of 2. Well, they're looking for what's the probability that x is less than 0.3. So let's say 0.3 is somewhere here. Well, now we're looking for what's the probability that we're between 0 and 0.3. So what's the probability that we're in that red shaded region? Well, now we're only going to integrate the curve between 0 and 0.3, because when you're integrating the curve with respect to the x-axis, you're getting the area below the curve above the x and between your limits. All right, so what we're going to get there for part 2. Now I'll rub out that curve again. I was just kind of explaining that that's what we're kind of looking at. So we'll have the probability that x is less than 0.3. Well, that's going to be equal to, we're integrating now from 0 to 0.3 of 2e to the minus x dx. So now that's exactly the same as what we did before. We do our integration and we fill in our limits. And that's around about 51836. I'd usually give your answers correct to, maybe I was going to say 4, then I was just going to write 3. Give your answers to correct to maybe 4 place of decimals, I would say. All right, because that's usually what's given in the tables as well. So that's part 2. And then I never checked in for questions, so I'll just check for questions and have a think about part 3 while I'm just going to check for questions. All right, calculate the median value of x. What do they mean, median? Right, they want you now to find what's the median value of x. So the median value, right, we're going to say that that's the value such that the probability of x being bigger than it, let's say, is equal to what? And I'll let you just have a think about that for a second. And I'm just going to check. All right, so I don't see any questions. How did I go from 2 to the minus 1 to 2 in the middle column? 2 to the minus 1 to 2. Yeah. Okay, so what I did there, I'm just going to talk about how I went from 2 to the minus 1 to 2, how I went from this line to this line. Okay, and I'm just going to put that on the next slide. So minus b is ln of 2 to the minus 1. So what I had there was minus b was the natural log of 2 to the minus 1. Okay, in your log tables, there's a rule that would say the natural log of a to the power of p can be written as, so if I have the ln of a raised to some power p, that p can come down in front and it can be written as p times the natural log of a. All right, so that what I'm getting here is I'm bringing that's kind of like my p, and I'm going to be bringing it down in front using that rule of logs. So we end up getting then that minus b is equal to minus 1 times the natural log of 2. And so then I'd have that minus b is minus the natural log of 2. So b must be the natural log of 2. And that's from that's a rule of logs. That's where I got that from. Yeah, but that was a good question. I'm just going to check that that was what you, how did I go from 2 to the minus 1 to 2? Yeah, I think that was, yeah. So look, hopefully that answers your question. You might just let me know if that answers it, and I'll check the chat again in a second. So that's what I used there, just to go from 2 to the minus 2 to 2. Okay, and the median, right? So what's the median? So the median is the halfway point, right? So it's the value of x such that the probability of being bigger than it should be 0.5. Now, you could equally say, well, it's the value x, let's say, such the probability of being less than it is 0.5. I'm just going for greater than it. You could go either way. All right, so it's the probability that the value such that the probability of being greater than x is 0.5. Now, again, if we're talking about being greater than x, then I'm going from x to b, because we're only going between 0 and b. It's only valid, this density function is only valid from 0 to b. So I want to go from then some value x that we're trying to find, because that's the median value we're trying to find. So the probability of being between this halfway point and the end point, which is b, but now we figured out what b is from part 1. We figured out that b is the natural log of 2. Well, then the integral from x to the ln of 2 of my f of x function should be 0.5, because I'm trying to find what is this value such that the probability of being above it is 0.5. That would give me the halfway point then. All right, so it would give me the median value of x. So again, we do our integration as before. So you're getting, that's going to give me minus 2e to the minus x, and then we want to evaluate that from x to the natural log of 2. And our answer should be 0.5. So we have to try and figure out what x is. All right, so we fill in our top limit, minus 2e to the minus the natural log of 2. And then we get minus minus, which is plus 2e, and we're filling in x, so we just have our minus x is equal to 0.5. And now what we want to do is we want to solve that for x. Okay, so I'm going to kind of do what I did before now. I'm going to say that that is minus 2e to the, now I'm going to just say minus the natural log of 2. See if we have again minus the natural log of 2. That is like having that minus is like a minus 1. So what I'd have there is that would be the same as, well, now that can come over and become the power. So that's the same as having the natural log of 2 to the minus 1. Okay, so I'm going to put that back here, which is the natural log of 2 to the minus 1. And then we still have plus 2e to the x equals 0.5. And then we're going to get, well, you see now, e, well, I'll just do one more thing. We'll have minus 2e to the natural log of, well, 2 to the power of minus 1, using this rule again. You know, we have x to the minus m is 1 over x to the m. So 2 to the minus 1 is the same as 1 over 2 to the 1, so that'd be a half. And then e to the natural log of a half, well, e and ln are inverse functions, so they're going to undo the action of each other. And what I end up getting there is the e and the ln will cancel out, so I get minus 2 times a half plus 2e to the x is equal to 0.5. Now, just to remind you, the natural log of e to the x is the same as e to the natural log of x, which would just give you x, because e and ln are inverse functions and they cancel each other out. So there's 3 kind of rules that I made use of there. Okay, and so then we get minus 1 plus 2e to the x is equal to 0.5. And I'll finish that on the next slide. Oh, and I'm putting equals all the way down along there when it was actually equal to 0.5. Okay, and I'll just finish it here. Part 3, continued. So we had that minus, so 2e to the x is equal to 1.5. Should be a minus. Okay, so it's 2e to the minus x is 1.5. We get e to the minus x then is 1.5 over 2. And so we have e to the minus x is, that's 0.75. And remember, we're trying to find x, because we're trying to find the value of x such that the probability of being bigger than it is 0.5. So we're trying to get x on its own. So again, we're going to have to get the natural log of both sides. So we end up getting there then that minus x is equal to the natural log of 3/4. Okay, so which means that x must be equal to, now, minus the natural log of 3/4, which would be the natural log of 3 over 4 to the minus 1. which would be the upside down version of that. So x would be the natural log of 4 over 3. And then that's approximately, so ln of 4 over 3, 0.2877. All right, so around about 2877. So now that is your median value of x. That is then your median value. All right, so far, the conditional probability, Bayes' theorem, so the total law of probability, or the law of total probability, conditional probability, Bayes' theorem, for a function to have a valid density function, the integral from a to b of that function must give you 1. Okay, and then the median is the halfway value. So it's the value of x such that the probability of being bigger than x is 0.5, or the probability of being less than x would be 0.5. Okay, and I think that's it then, apart from some rules of logs that also came up there. Okay, now part C, we have that a factory repairs mechanical parts where 80% of all parts received can be classed as easy to repair and the remainder are difficult. All right, so I'm just going to start making some kind of notation. Now, sometimes you're given notation and you are supposed to use the notation then. So T is the random variable, right, representing the repair time. And we assume that the repair times for easy and difficult are exponentially distributed. Now, this is coming from the formulas that you're given on the back page of the exam. So I just put down the exponential distribution there because we'll need it for this one. So first of all, they're telling me that a factory repairs mechanical parts. 80% of all parts can be classed as easy to repair. So the probability that a part is easy to repair is, well, it's 0.8 because they said it was 80%. And the probability that it's difficult to repair is 20%. Okay, so that's just the first piece. Now they said that T, well, they did say, assume that on average, all right, so assume that on average, okay, so assume that on average. Now, if they say on average, what they're talking about there is the mean or the expected value, right? So I'm just putting the expected value. Now I've called it X, but actually I think that would be E of T really. That would be E of T because it's time, but I've just put the mean or expected value. So you need to be thinking, if they say assume that on average, well, now you're talking about the mean or the expected value. And now in a minute, we might be looking at, you see, the expected value here, E of T, is 1 over lambda. And you know, in actual fact, I might just leave that be E of, no, I leave it be E of X for now because I was just kind of talking in general when you're reading the question. So on average, the mean or the expected value of X is what you're thinking of there. So easy repair jobs take 15 minutes to process. Okay, now they told us that T is a random variable representing the repair time and that for both easy and difficult jobs, it's exponentially distributed. Okay, so then I would be saying that the time, given that it's, let's say, an easy job, is exponentially distributed. And we'll say with parameter lambda E, we'll call it lambda E. All right. Now, so that means that the time for an easy job then is exponentially distributed. And then what is the mean? So it says on average, easy jobs take 15 minutes. So on average, easy jobs take 15 minutes. Okay, easy repair jobs take 15 minutes. So I'm going to say then the expected value, right, of the time, let's say, to repair an easy job is 15 minutes. That's what they told us, you know, and I'm just saying the mean, they told us the mean, right? So the mean for an easy job, mean for easy is 15 minutes. So that means the expected value of the time, given that it's an easy job, is 15 minutes. But they told us, right, that it's exponentially distributed. So therefore, we know that the expected value of time, if we're talking about an exponential distribution, the expected value is 1 over lambda. Okay, so then I can say that the expected value of the expected time, if it's an easy job, is 1 over lambda. So we'll say it's 1 over lambda e. Now I want to know what lambda is. So I know what the expected value is. They told us the expected value, we can fill in, the expected value is 15. And that must be equal to 1 over lambda e. And therefore I can say that lambda e must be equal to 1 over 15. So now I can put that here. 1 over 15. Right? So the expected value, it says on average, easy jobs take 15 minutes. So that's the expected value. So then what's lambda? Well, the expected value is 1 over lambda. That's 15. So 15 is 1 over lambda. What's lambda? Lambda is 1 over 15. And then exactly the same for the difficult jobs, right? The time, given that it's a difficult job, we can say again is exponentially distributed, but now we'll just call that lambda d for difficult. And then that means that the time, if it's a difficult job, is exponentially distributed. And this time, what did they say? That the difficult jobs take 30 minutes to process. So that's going to be 1 over 30. So now I have a couple of bits of information. We have the probability that it's going to be, the probability that you have a part is easy to repair is 0.8, probability it's difficult is 0.2. And then we have that the time for an easy part, it's an exponential distribution where lambda is 1 over 15, and for difficult it's an exponential where lambda is 1 over 30. Okay, so I've only just read the question. I mean, I've only read the information in the question and tried to sort that out. And I tried to use the notation that we were given that t is a random variable. All right, now part 1, I'll just write down part 1 and I'll check if there's any questions before I move on. Part 1 says, find the probability that the time taken to repair, because t is the random variable representing the repair time. Hello? Did you have a question? Or maybe you just okay. So the probability of the time being greater than a particular value, right? So what's the probability that the time is greater than, let's say, some value t? They want us to find that. Now, we're talking about an exponential distribution. So I have the formula anyway for that. It's up here, right? The probability that it takes longer than a certain time is e to the minus lambda t. All right, so I'm going to say, all right, that's equal to e to the minus lambda t. So that's in general the formula we'll be using. But see, we've two things going on here now. So the probability that it takes longer, so the probability that the time taken is greater than some value t. Well, either the time is greater than t and it's an easy job, or the time is greater than t and it's a difficult job. So just have a think about how we're going to write down our next line for this. And I'm just going to check if there was any comments in the chat again before I move on. Yeah, okay, that answered your question. That's perfect. All right. So we're looking for the probability that it takes longer than a particular time t. And we just went to our back page of the formula, or the back pages, we found, okay, it's exponentially distributed. So that's going to be e to the minus lambda t. But we've different lambdas depending on whether we're talking about an easy job or a difficult job. All right, so I'm just going to write down the formula on the next slide. So for part 1, we're looking for what's the probability that the time taken to repair, or the repair time, is greater than some value t. Well, then I'd be saying, okay, that is going to be the probability that it takes longer than some time t and the job is easy, or, so for or I'd be saying plus, the probability that the time taken is longer than t, and it's a difficult job. And then let's go back to what we looked at the very beginning, was that conditional probability. Okay, so do you remember that I was saying, I might just remind you of it here again, that let's say the probability of A, given that B has happened, is the probability of A intersect B all over the probability of B. So if I wanted to just get the probability of A intersect B on its own, then it's the probability of A given B by the probability of B. That's just a reminder of the formula. So I'm going to use that same formula here again that we used at the beginning. So the probability that T is greater than T and it's an easy job, well, that is the probability that T, so this is kind of like my, this is like my A now, if you like, and this is like my B. So it's like A intersect B. So it's the probability of A, which is T is greater than a particular time, given B by the probability of B. And the same for this, then we'll get plus the probability of A given B times the probability of B. And we should be able to fill that in now. So the probability that T is greater than T, given that it's an easy job. Now, we already said that for the easy job, right, we called it lambda E. And for the difficult job, we called lambda D, right? So the probability, there's my formula in general, right? The probability that T is greater than T is e to the minus lambda T. It's e to the minus lambda T. So the probability that T is greater than T, if it's an easy job, is going to be e to the minus lambda ET. Okay, so we're going to get there e to the minus lambda ET by the probability that it's an easy job. Well, the probability that it's an easy job was back here. The probability that it's easy is 0.8. Okay, plus, and just to remind you, you see in the back pages of the exam, we had the probability that T is greater than T is equal to e to the minus lambda T. So if I wanted then, let's say the probability that T is greater than T, given that it's an easy job, well, our lambda for the easy job, we called it lambda E. So we just replaced lambda E with lambda. And we're going to do the same here. We'll replace lambda D with lambda. And then the probability that it was an easy job was 0.2. Okay, and so we end up getting there then. And what was lambda E? Lambda E was 1 over 15 and lambda D was 1 over 30. So we get here 0.8 e to the minus 1 over 15t plus 0.2 e to the minus 1 over 30t. And that's your answer for that part. All right, that was part 1. Part 2 says, what's the probability that it's an easy job given that it takes longer than that particular time? So what's the probability that it's an easy job given that t is greater than t? So part 2, probability that it's an easy job given that t is greater than t. Well, again, we're going to use our conditional probability. That is the probability that it's A. So it's asking you here, probability of A given that B has happened. So it's the probability of A intersect B all over the probability of B. Okay, and we can use our answer now from part 1 to fill in to the denominator there because we just figured that out. So we're going to use the answer from part 1 here. So we end up getting, right, what's the probability that it's easy and it takes longer than a time t? Well, we have that as well, actually. Easy intersect time greater than t. That's that first part. So what we have is we've all the parts worked out for ourselves already. It's 0.8 e to the minus 1 over 15t all over the whole lot. And that's that. Do you know, I would, yeah, I think you could leave it like that. Now you could factorize out maybe the bottom. Yeah, I'd leave it like that for now. That's part 2. And then part 3 says, and hence, okay, so we've just done part 2 and now they're saying, and hence, find the value of t such that the probability that it's an easy job given that t is greater than t is 0.6. Okay, so now they want us to take the answer for part 2, put it equal to 0.6 and find the value for what t is. Okay, and I'm just going to put in an extra slide. Okay, so take the answer from part 2 and put it equal to 0.6 and solve for t. So part 3 says the probability that it's an easy job, given that the time is greater than some particular value t, is 0.6. Well, then what's t? Well, we already have that worked out from the last answer. So I'm just going to put that final line there equal to 0.6. So I get that 0.8 e to the minus t over 15 all over the total. And that must be equal to 0.6. And you want to solve there for t. All right, so I'm just going to cross multiply. T of 15. Okay. All right, so 0.6 by 0.8 is 0.48 e to the minus t over 15. And 0.2 by 0.6 is 0.12 e to the minus t over 30. Okay, and then I'm just going to bring these two guys to the left-hand side. So 0.8 minus 0.48, that's 0.32 e to the minus t over 15 is 0.12 e to the minus t over 30. And so then I get that e to the minus t over 15 all over e to the minus t all over 30 is going to be 0.12 over 0.32. Now again, do you remember your rules of indices? So if I've got two, we say two terms, they have the same base and I'm dividing, well then we subtract. So that's going to be e to the top index minus the bottom. Right, that's from your rules of indices. That's going to be equal to 12 over 32. So it'll be 3/8. And then we get e to the minus t over 15 plus t over 30 must be equal to 3/8. So e to the minus t over 30 is 3/8. And remember now we're trying to get t again by itself. So we're going to have to, whatever, you know, t is there, it's in the index or power position, we're going to have to use logs. So we just bring in the logs of both sides. And then using that rule again, that we can bring down the power and multiply it in front of the log. That rule is after coming up a couple of times actually already in this. So we're going to get then minus t over 30. Well, the natural log of e is just 1, is the ln of 3/8. And so we get then minus t is going to be 30 times the natural log of 3/8. And so t will be minus 30 times the natural log of 3/8. And we wanted to get, you know, what is the value for the time then. So if you put that in your calculator, minus 30, the ln of 3/8, 29.42. So 29.4248, so you say 0.42 minutes. All right, so it's about 30 minutes. So the probability that it was an easy job, given that the time was longer than 30 minutes, is 0.6. Or that's an easy job, given that the time is longer than 29 minutes. 0.6. Yeah, because on average it was saying that an easy job should only take 15 minutes, but there's 80% of the repair jobs are easy. All right, so that's why it's a bit bigger than what you might think. You know, like if they said that on average it takes 15 minutes to do an easy job, well, then the probability that it's an easy job, given that our time worked out to be nearly 30 minutes. What's the probability that it's an easy job, given that it nearly took 30 minutes to do it? And they told us the probability was 0.6. That seems kind of high when they told us that on average it should only take 15 minutes, you know, to do an easy job. But it's because of, as well, 80% of all of them are easy jobs to do, and that's what makes it a bit bigger there. Just in case that you were saying, you know, logically that might have made a huge amount of sense to you. All right, so that's on to question 2 then. We have the probability. Now I think the second part of question 2 is a bit quicker than maybe I spent a bit too long on question 1, but I just I don't want to rush anything. That I'm hoping that you're kind of writing it as I'm going through it as well, that you're trying it yourself. Okay, so this one, it can be shown that for x being binomial, so for binomial distribution, NP, right, the moment generating function is given by, and they've given us what it is there. All right, so there's your moment generating function, and they're not asking you to derive it, and they're asking us to use it to show that the expected value, so that the mean of the binomial should be n times p, and the variance is np times 1 minus p. So I'm just going to write down some things here that we're going to need. Okay, so we have the moment generating function anyway is the expected value of e to the xt by definition. That's what the moment generating function is. Now the kth moment, okay, if I wanted to find what is the kth moment, I would differentiate the moment generating function and evaluate it at 0. And that would give me the kth moment. So it's the expected value of x to the k. Now, if I want the first moment, which very often we're looking for the first and the second moment. So the first moment would be get the first derivative of the moment generating function and evaluate it at 0. And that is the expected value of x. So the first moment is the first derivative of the moment generating function evaluated at 0, and that is the expected value of x. Okay, and then your formula for the variance of x is the expected value of x squared minus the expected value of x all to be squared. And what I'm just writing down there, that's given on the back page, that variance of x. So we're going to have to find out what is the second moment. The second moment. So the first moment is the first derivative evaluated at 0. The second moment is the second derivative. So we differentiate the moment generating function with respect to t, evaluate that at 0, and that gives me the second moment, which is the expected value of x squared. And then I can use, you know, the second moment with the first moment to try to figure out what the variance is in a minute. So I'm going to be coming back to that right-hand column there now. So first of all, they asked us to show that the expected values is NP. So we start off and say, okay, they gave you the moment generating function. Here it is. It's e to the t times p plus 1 minus p to the power of n. Now, I want to find out what is the expected value of x. So we want to show that the expected value of x is NP. Well, we know how to get the expected value of x. It's the first moment. So I have to differentiate the moment generating function with respect to t and evaluate it at 0. So we will first of all differentiate it with respect to t, and then we can fill in the 0 after. Okay, so to differentiate this with respect to t, I'm going to use the short chain rule. So I'll bring down my power of n, leave what's in the bracket alone, reduce the power by 1, and then we multiply by the derivative of inside the bracket. Okay, so if I multiply by the derivative of inside the bracket, remember now we're differentiating with respect to t. So the 1 minus p will just go to 0. And then the e to the tp, that will just be e to the tp. Right, because e to the t goes to e to the t. So if I had 3e to the t, the derivative of that would be 3e to the t. And so we just tidy that up. So I'm just going to I'm going to multiply the e to the t times p by the n. So we're going to get np e to the t times e to the tp plus 1 minus p to the n minus 1. Right, that's the first derivative. And we wanted the expected value of x, which is the first derivative, evaluated at 0. So I'm putting in 0 everywhere for t now. We'll get np e to the 0, e to the 0 times p, 1 minus p, n minus 1. E to the 0 is 1, so I'm getting n times p, p plus 1 minus p to the n minus 1. So we get np, and 1 to the power of n minus 1, well, 1 to the power of anything is just 1. So we get 1 to the power of n minus 1. So we get np. Perfect, right? Because that's what we wanted. The expected value of x is n times p. Right? So how do I get if they've given you the moment generating function, and they've asked you, show that the expected value is np. Well, to get the expected value, it's the first moment. The first moment, we get the first derivative and evaluate it at 0. They also want you to find the variance, right? So they said, show that the variance of x would be np times 1 minus p. Well, we know what the expected value of x is. So in a minute, I'll want to get, what is this variance? We already have the second part, the expected value of x is np. So I'll be just filling in np to be squared there. But we need to get the expected value of x squared. That's the second moment. So we need to go and differentiate this again and evaluate it at 0. Now, we're going to make use of the first derivative. Well, we already found the first derivative, so I'm going to write that down again. That's what we got for the first derivative. So I'm going to start with that on the next slide. Oh yeah, I robbed a slide a while ago, didn't I? So okay. Okay, so I'm just going to write down what the derivative was again. So we had the first derivative. So the first derivative of the moment generating function turned out to be np e to the t times e to the tp plus 1 minus p. E to the t times p plus 1 minus p to the n minus 1. Now we're going to have to get the second derivative, right? So that was the first derivative. We now want to go and find the second derivative, and then we want to fill in 0, and we'll be able to use that then to find our variance. Now, what we have here is we have a function of t being multiplied by a function of t. So we have a u by v, okay? So it's the product rule. So we're going to use the product rule. So it's u dv dx plus v du dx. Okay, so it's going to be u, which is np e to the t. So it's u dv dx. Now that's what we did before. So it's u times, one sec there, I'm just going to. Sorry, just took off the earphones so I wouldn't be coughing into your ear. Okay, so that's u dv dx. So we want to differentiate this, but we did that before, the short chain rule. So we bring down our power, leave what's inside the bracket alone, reduce the power by 1, times the derivative of inside the bracket. So that's u by the derivative of v plus v, which is e to the t p plus 1 minus p to the n minus 1. So u dv plus v du. So differentiate np e to the t. Well, e to the t just goes to e to the t. So we get np e to the t. And now we have to try and tidy this up. Now I wouldn't get too bogged down in it, right? Because we just have to differentiate it and then fill in the 0. So I wouldn't go tidying it up a huge amount, but just maybe a little bit. So we're going to get, let me see. So we have pe to the t, and I have another pe to the t, and I have an n times an n minus 1, right? So I'm just going to write that then as n times n minus 1 times pe to the t 2b squared times e to the t p plus 1 minus p to the n minus 2. Right, that's just the first part. I tidied up a small bit. And the second part, I think I'm just going to bring this part in. So we're going to get n p e to the t times e to the t p plus 1 minus p to the n minus 1. I think that's all right. All right, so what we can do then is just fill in our 0, because we just want to figure out what the second derivative is evaluated at 0. So mx, we're now going to fill in 0 for t. So we get n times n minus 1 times, now e to the 0 is just 1, so I'm just going to get p squared. E to the 0 is 1, so we get p plus 1 minus p to the n minus 2 plus n p e to the 0 is 1 times e to the 0 is 1 n minus 1. So what we end up getting there then is n times n minus 1 times p squared. Now p minus p is gone, and 1 to the n minus 1 is just 1. And then I'm just going to get plus n times p, because all of this again, see, p minus p is 0, and 1 to the power of anything is just 1, and 1 multiplied by the np will just still be np. So that's what we get for the second derivative evaluated at 0. So now that is the second moment. That's the second derivative evaluated at 0. So that is the expected value of x squared, or the second moment. And then we said, well, the variance of x is equal to the expected value of x squared, the first moment, minus, sorry, the second moment, minus the, oh, now why did that happen? Minus the expected value of x, or the first moment, all 2b squared. So we end up getting now the second moment just turned out to be n times n minus 1 p squared plus np minus, and the expected value of x, well, we got, it's np, right? The expected value for the binomial is np. And so we end up getting there, multiplying that out, we get n squared minus n times p squared plus np minus np squared, and that would give us n squared p squared minus np squared plus np minus n squared p squared. So n squared p squared minus n squared p squared is gone, and we end up getting, that would be equal to, and I'll just take, well, I'll put the positive first. It's np minus np squared, and then take out an np into 1 minus p. And that's what we wanted. The variance of x is np times 1 minus p. And that's that done. All right, so that just goes back. Now it is differentiation, but just remembering that you're differentiating there with, there's a lot of variables going on, so you're differentiating there with respect to t. And that's part A done. Okay, and I'll just write, now B, they've given you 4, right? So they've given you 4 questions, and they said clearly state what's the distribution that you're going to use, and then answer the associated short questions. So these are shorter questions than the one that they gave you in question, well, in question 1 maybe. All right, so the questions will be a little bit shorter. But we'll see how we go through them. All right. So the very first thing is you want to read the kind of scenario and decide, okay, what distribution does this look like? Now, before I'd even then go, if I saw this question in an exam and let's say I was kind of a bit iffy about my distributions, I'd say, okay, let's open up the back page anyway and remind me, what distributions do we have? All right, so here's some, right? We have the binomial, geometric, Poisson, so there's your discrete distributions. And your continuous distributions, then the exponential, the uniform, and the normal. Okay. Now I'm going to talk about the geometric has a relationship to the binomial, the same as what the exponential has to the Poisson, but I'll talk about that in a minute. So before I say anything, have a read of the first one and just say to yourself, okay, what's that looking like to you? Would it be, which one of these distributions are you thinking about? Binomial, geometric, Poisson, exponential, uniform, or normal? All right, have a read of the first one. Okay, because sometimes the hardest part of this is picking the right distribution. Okay, so glass sheets are produced containing blemishes at a rate of 1 per meter squared. So we have the number of events in a particular interval of time or distance or area in the first sentence. Okay, so I'm just saying glass sheets are produced containing blemishes at a rate of, so I have at a rate of 1 per meter squared of glass. So what I'm just even thinking of in English so far is like the number of events in a given interval of time or it might be distance, or it might be, area or some kind of space. Okay. Some kind of space. That just sounded funny. So if you're thinking about the number of events in a given interval of time, distance, or area, you're thinking about the Poisson. Now you might say I wasn't thinking about the Poisson at all. Well, then you just need to go back over, your distributions, because you'd say, okay, right, they're talking about the number of some type of events, in this case blemishes, are happening at in a given interval of time or space or distance or area. So what they're doing here is area at a rate of 1 per meter squared. So we know how many is happening in a particular interval of something, be it time, distance, or area. So that's Poisson. Now, let's say that X is going to be the number of blemishes. X is the number of blemishes, because that's what we're talking about in this question. And then we have, well, X is going to be then Poisson distributed. And you can go to your back page. Now we're saying it's Poisson, right? And so we have, it's Poisson, and we have, our parameter there is lambda. Now, they told us that, glass sheets are produced at a rate of, so that's the rate. So lambda is going to be 1 per meter squared. So they gave us that in the question. Lambda is 1 blemish per meters squared. And then they ask you, what did they say? A particular customer has ordered a 5 meters squared sheet, but they'll only accept it with 2 or fewer blemishes. What's the probability that they're going to accept it? So that's the question then. They've ordered a 5 meters squared, but they're only going to accept it with 2 or fewer blemishes. And so what's the probability that they're going to accept it? Okay, and I'll just put that up here. So the first thing is I'm going to look for the probability that, x is 2 or less. They said 2 or fewer. So I want the probability that x is less than or equal to 2. All right, that's what we're going to be looking for. But if you look at your Poisson distribution, we have that the probability that x is equal to x is equal to lambda to the x over x factorial e to the minus lambda. So I'd write that down for myself. Right? I'd say, well, the probability that x is equal to, so let's say the probability that there are 6 blemishes, right, would be equal to lambda to the x e to the minus lambda all over x factorial. So that's my formula that I'm going to be making use of. But now remember, right, they're talking about a 5 meter squared sheet. So if the rate is 1 per meter squared, well, then in 5 meter squared, you'd have 5, right? So it's 5 per 5 meters squared. And so therefore, then I want, what's the probability that there's going to be 2 or less blemishes? So that would be the probability 2 or less is none or 1 or 2. And if you're thinking about or, the word or is adding, and the word and would be multiplying in probability. All right, so we just fill in then, what's the probability that x equals 0? Well, we fill into our formula here. That's going to be lambda, but lambda now is, see, it's 5 per 5 meters squared. So lambda is 5. So we're going to get lambda, which is 5, to the x, which is 0 in this case, e to the minus 5, all over 0 factorial, plus lambda, which is 5, x, in this case is 1, e to the minus 5, all over 1 factorial, plus, and then 5 to be squared, e to the minus 5, all over 2 factorial. So I'm just going to take out e to the minus 5, and that'll be multiplied by 5 to the 0 over 0 factorial, 5 all over 1 factorial, and 5 squared all over 2 factorial. Right, so that's e to the minus 5 times 1 plus 5 plus 25 over 2. Okay, and then that should give you approximately 0.1247. Okay, now what about the second one? I'm just going to, so you read the second one, I'm checking the questions or the chat. 2019. Yeah, sorry guys, I just saw that now. So 2019 is the exam paper. I do have it on the front of the, I do have it on the slides at the front. This is 2019. Okay, so the second one, a battery charge cycle is the process of fully charging a discharged battery. So at each cycle, there's a constant probability that the battery fails. If the average number of cycles to failure is 500, okay. So now, first of all, when I started reading that, you might be starting to think about the binomial because you're saying, okay, fully charging and discharged. So there's a constant probability that it will fail. So you might be thinking, okay, well, it'll fail or it won't fail. Okay, and then you might be thinking binomial because you know the way the binomial has only 2 outcomes, success or failure. But then it starts talking about if the average number of cycles to failure is 500. So if the average number of cycles to failure is 500, what's the probability that the battery lasts more than 800? So now they're telling you that on average, it'll go through 500 cycles before it fails or until it reaches its first failure. All right, and so what I would be saying is if you're starting to think about the binomial, okay, the binomial would say, what's the probability that there are, let's say, 7 fails in 20 trials or something like that. But if they start talking about the number of trials until the first failure or until the first success. So the number of trials until you get, you know, the first failure or the first success. Now you're talking about the geometric. And as well, we just looked at the Poisson in part 1 when you're looking at, you know, the number of events in a given interval. Well, if you're looking for the amount of time until we reach the first Poisson event, that's the exponential. So the amount of time until we get to the first Poisson event. So the exponential is to the Poisson what the geometric is to the binomial. Okay, so if I'm talking about, we'll say if we're thinking kind of like a binomial distribution, we're talking about either the battery will fail or it will not fail. If we're talking about the number of trials until we get to the first failure, now we're talking geometric. And if we had a Poisson, let's say the number of blemishes, what's the probability that there are 2 or fewer blemishes? Well, we're talking Poisson. But if we said, what is the probability that we've gone through, let's say, 6 meters squared before we get to the first blemish? Now we're talking about the exponential. Okay, so in part 2, they're talking about the average number of cycles to failure. Now watch out for that word, average. We already came across it. That average means the mean or the expected value, right? So the mean or the expected value is what they're talking about there. So part 2. So you need to read these things really carefully because sometimes they're a little bit hidden. So the average number of cycles to failure, they told us, is 500. And I'm underlining the word there, average. The average number is 500. So I'm going to say, well, let x be then, it's the number, let it be the random variable depicting the number of cycles until we get to failure. Cycles to failure. And so now I know that x must be its geometric distribution because we're talking about the number of cycles until we get or to the first failure. So it's geometric, and again, you see it's geometric with parameter p. Now, they were talking about the average number of cycles. Average. Now we're talking expected value. The average number, they said, was 500. Okay? And so that means the expected value is 1 over p. Right? So the expected value is 1 over p is 500. So what's p? P then must be 1 over 500. And we're going to need that in a minute because they're probably going to ask us something about what is the probability about something. So let's have a look. It says, what is the probability that the battery lasts more than 800 cycles? So we want the probability that the battery lasts more than 800 cycles. So it wants to be greater than 800 cycles. Okay, and if we look at our formulas here, we have the probability that x is greater than or equal to x is 1 minus p to the x minus 1. Well, if it's greater than 800, that means it must be greater than or equal to 801. Okay, and so now we can say, well, the probability that x is greater than or equal to 801 using the formula that I just boxed off there, and you are given all these formulas, that will be 1 minus p to the x minus 1. Now, 1 minus p, well, p is 1 over 500 to the x minus 1. Well, in this case, our x is 801. Subtract 1. So we end up getting there 1 minus 1 over 500 to the power of 800. And then that's approximately 0.2016. Now, to be honest, I think the hardest part of this particular question is figuring out, no, not that it's the hardest part, sorry, because I mean the rest of it isn't so, it's figuring out, right, what distribution are you using? And that can be kind of tricky, because sometimes it can start sounding like a binomial, but when they start talking about, the number of cycles to failure, and then you can very quickly start thinking it's geometric, but they're telling you they're the average number of cycles to failure. They're giving you the expected value of a geometric. And honestly, that's not always so clear to see when you're reading these. So it's kind of even getting practice at just kind of getting those clear in your mind, which distribution. So that's one, that's two. Now three, assume that 35% of people have the blood type A positive. In a sample of 100 randomly selected people, what's the probability that more than 30 of them have this blood type? So now we start thinking about number three. What things have you been given, and which distribution do you think that starts to look like? So 35% have the blood type A positive in a sample of 100. So now I'm reading this and I'm saying, okay, I know what the probability is that someone has blood type A positive. It's 0.35. Now they're telling me there's a sample of 100 randomly selected people, so I have a total number of repeated trials is what I'm thinking. What's the probability that more than 30 of them have the blood type? Okay, now I'm thinking binomial because, number one, I might just write this down. So the reason I'm starting to think binomial is there's 4 conditions for the binomial distribution. So part 3, number 1, right? A fixed number of repeated trials. I'm sorry, I'm using that. He'd say he'd say hashtag, and of course I'm that much older that I would just say that's a sharp in music, right? Or a number. So I'm using that for a number, right? Even though now in fairness I do know it's hashtag, right? So fixed number of, I just never use it that way. Repeated trials, all right? So there's a fixed number of repeated trials. Now in this question for part 3, they did tell us in a sample of 100 randomly selected people, so there's my repeated trials, N is 100. The second condition, there's a fixed probability of success. Fixed probability of success. Now, I mean, you can decide what your success is. So we'll say, okay, the probability of having A positive is a success in this case. And they told us, I think it was 35%. Yeah, 35%. So there's my fixed probability of success. It's known. So that's one. There's a fixed number of repeated trials, fixed probability of success. Now, trials are independent of each other. So, I mean, if I come along, independent, dependent. If there was a group of 100 people, or as opposed to just independent, then the chances, like if one person, if I pick person A and B have A positive, well, the probability that the next person has A positive, given that the other person had it, there should be no relationship. Now, assuming that there's not family members in that group. So 4, and this is probably the one that you've recognized the most, there's only 2 outcomes. That's probably what makes you start thinking about the binomial straight away. Only 2 outcomes per trial. Either they're going to have A positive blood or they're not. So that's what makes me think binomial, right? First of all, I know what the probability of having A positive is, 0.35. We have a fixed number of how many people we're going to ask, 100. That's a fixed number of repeated trials. And then trials are independent of each other because they said randomly selected people, so they're not related. Or at least, if they're randomly selected, well, they could be related, but I mean, it's random, so they should be independent. And what is the probability that more than 30 have the blood type? Okay, so now we're talking binomial, and we're looking for what's the probability that more than 30, X is bigger than 30. Okay, now when you go to your tables, you get the probability of or more, so you'd be getting there the probability that, I suppose, or more successes. So when they ask you that X is greater than 30, using our tables, we're going to have to say that that's the probability that X is greater than or equal to 31. And if we go to the tables, now we have N is 100, P is 0.35, and R is 31. So you have, N is 100, P is 0.35, and R is 31 in your tables. So N is 100, P is 0.35, R is 31, there's 31. And going across there then, we get 0.8270. All right, so P is across the top, N is coming down N is 100 at the left-hand side there. We have N is 100, P is 0.35, and R is 31. Now, I think you're after switching to new tables, but I didn't have that particular version, but I will have it for the, for our final exam, but just make sure that you can get that value from your tables. So that's part 3. And then part 4, so in your tables, part 4, last part, a roll of fiber optic cable contains somewhere between 10 and 12 meters of cable where all values in the range are equally likely. Okay, so equally likely. So now I'm seeing all values in a continuous range, equally likely. That's making me thinking about the uniform. Okay, equally likely continuous values on a given range is the uniform distribution. So part 4, I'm going to say equally likely continuous values on a given range. That's the uniform distribution on A to B. Okay. And we'll go back then. So they said a roll of fiber optic cable contains somewhere between 10 and 12 meters. Okay, so we're talking about the length. So I'm going to say X is representing the length of the fiber optic cable. Now, X is uniformly distributed because we're talking about equally likely continuous random values on a given range. There's my X is uniform on AB. That are my parameters A, B. So for us, we know X is uniform on, and they said between 10 and 12. In the question, they said between 10 and 12 meters. Okay, so an engineer requires at least 10.6. What's the probability that the requirement will be satisfied? So what's the probability that it's at least 10.6? Okay, so we want to say what's the probability that it's greater than 10.6? Right? Now, where's our uniform? And here, okay, the probability that it's at least 10.6. So the probability that X is greater than X is B minus X over B minus A. So that's what we're going to be needing to use. The probability that X is greater than X is B minus X all over B minus A. That's the formula we're going to be using in a minute. And so we want what's the probability that X is greater than 10.6. Now, I'm just going to put it up here as an aside. For the uniform, what you'd have is for that particular distribution that they're giving us, they're saying, okay, between 10, isn't it, and 12. Now this is just drawn it here. So let's say 10, 11, 12. Now you remember I was saying to you that for a valid, density function, we have to have that the area underneath there would have to be 1, right? The area would have to be 1. So if this width here, you see, is 2, well, that means that the height has to be a half, because a half of 2 would be 1, and then we'd have the total probability there would be 1. So the total probability all in here would be 1. So the probability would be between 10 and 12 is 1, because that accounts for all values of length. Okay, and what they're asking for is what's the probability that it's 10.6 or more? So let's say there's my 10.6. Oops. Let's say there's 10.6. So what's the probability that we're in that red shaded region? Okay, and then you can kind of see that it makes sense that it's b minus x, because it'll be 12 minus the 10.6 all over 12 minus 10. So it's like the probability of being within that kind of red region divided by the probability, divided by the total region. All right. So what we'll get there then is that's going to be equal to, following our formula, b is 12, x is 10.6, b is 12, a is 10. Because I had my a and b here. And then the probability that x is greater than a particular value x, there's my x is 10.6. So that gives me, well, 10.6, 1.4 over 2, which is approximately 0.7. So there was four different distributions, and you had to be able to recognize when to use which one. Okay. Now that leaves us. Yeah, I think last year I didn't get on to question 3 either, because I kind of took my time with them. But what we'll do is we'll just finish off the C part, okay? And we'll just do the C part, and we'll do question 3 tomorrow. Kind of might be better anyway, because I don't think not tomorrow, sorry, the next day it's on. I don't think we can do as much of the second section, so it'll work out okay time-wise for us. Assume that the number of emoticons, smiley faces, appearing in a tweet can be described by a binomial, right? N is equal to 20, P is equal to 0.4. Okay. Now, on average, how many tweets would you expect to have read when you first receive a tweet with more than 3 emoticons in it? Okay. Now, this is the questions, I will tell you this. I've seen however many exam papers of these, the questions are cleverly put, and they will always be cleverly put. All right. It looks like this is a binomial distribution from what we're starting off with. Assume that the number of emoticons appearing in a tweet can be described by a binomial. N is 20, P is 0.04 distribution. Fine, right? So I'll write that down. X is the number. This is the last one, and honestly, this would be short. So if you just bear with me for a couple of minutes, we'll be finished. I'll leave question 3 until the next day. So the number of emoticons in a tweet is binomially distributed, where n is equal to 20 and p is equal to 0.04. Okay, so the total number of repeated trials is 20, and the probability, that we have emoticons appearing is 0.04. So on average, and there's that word again, on average. On average, now we're talking expected value. In a minute, it'll be coming up. How many tweets would you expect to have read when you first read? And now, when you first receive, and that is the word until we get, to the one that has more than 3, until you get to the first one. So when you first receive. So now the red part is telling me I'm looking for the expected value. So on average means I want the expected value. And until we get to the first tweet with more than something on it. So until we get, that means I'm talking about the geometric. Do you remember I was saying to you the geometric is to the binomial what the exponential is to the Poisson. So that is the expected value for the geometric is what's coming up here next, even though it starts off with binomial. So there's a relationship between the binomial and the geometric, and there's the same type of relationship between the Poisson and the exponential. Okay, so let's call, we said XO is binomially, I already wrote that down. Let's call X, so X is the binomial, so that was the number of emoticons. Let's go for T, tweets. So that's going to be the number of tweets read until, so think of that word until, right? We first receive a tweet with greater than 3 emoticons. So T then is going to be geometric distribution, geometric, and I'm going to call it, PT. Okay, because if you go back to your geometric distribution, and you see, I would have these open anyway for yourself. The geometric, with parameter P, so we'll say PT. Now, I probably wrote that P a bit big. I'll just say PT. Okay. So what are we looking for? On average, they're asking me, how many tweets would you expect to have read when you first receive a tweet with more than 3 emoticons? Okay, well, if we're talking about the geometric, we'd be saying, well, the expected value would be equal to 1 all over PT, right? So if you go back to your distributions, the expected value, see here for the geometric, is 1 over P. So it'll be 1 over P. We're looking for, on average, how many tweets would you expect to have read when you first receive one that has more than 3. So I need to know what is that PT, and that is what is the probability of getting a tweet that has more than 3 emoticons, and that goes back to the binomial. Okay, so now we're going back to here. So what is the probability that I would have more than 3 emoticons on a tweet? Well, that would be, again, when we're looking at the binomial, we get the probability of or more. So greater than 3 is 4 or more. Okay, and again, now we want to go to the tables where n is 20, p is 0.04, and r is going to be 4. So now I have n is 20, p was 0.04, there's 0.04, and r is 4 or more. So 4 or more, and then line those up. So it's going to be 0.0074. 0.0074. Now that's the probability of getting a tweet that has more than 3 emoticons. So now the expected value on average then, how many tweets would you expect to have read until you get to the first one that has more than 3? So that's 0.0074, and then that is 135.13. So that's the expected value there. So on average, you'd expect to receive 135 tweets until you receive one that has more than 3 smiley faces. Receive a tweet that has greater than 3 emoticons. I suppose it's probably unusual, depending. I suppose it depends on the person. So you'd expect to have 135 tweets until you'd receive one that has more than 3 emoticons. Now, don't worry that we didn't get to question 3. What is coming up next, I'll just show you. For question 3 is it's going back to the normal distribution. So what would be a good idea? I think it's Thursdays the next time we have this class. So question 3 is find the probability that x is less than 25. So we'll give you a normal distribution with a mean of 20 and a standard deviation of 3. Find the probability x is less than 25, probability that x is between 23.5 and 28.4. The first 2 parts are using your tables and using, standardizing back to the standard normal. The third part is using your tables kind of backways. And the fourth part is have a look up about the central limit theorem. All right. And then that would be question 3, part A. Part B is actually very short. Part B will take us about a minute because it's just theory. And then we can't do part C anyway. So actually, all we would have left is about another maybe 20 minutes would sort that out. All right. We'll do that the next day. And then I'll move on to question, well, 4 and 5. I don't know actually, are they called question 1 and 2 in the, are they, they're, you know, I think it repeats again into a new section. So I think, do they call them? Yeah, he does. He calls them question 1 and 2 again. So in question 1 would be statistics. So you're talking about the mean, median, mode, histogram, confidence intervals. And then I want to do some hypothesis testing maybe. We'll only probably do, yeah, question 1 and 2. I don't even know if you've all question 2 done. Okay. You know, yet I'm just going to check because I emailed Kevin just to check how much you have done, and we'll just cover what you've done. Guys, I hope that helped somewhat. And I'll, you know, the attendance will come up, so I'll be able to save who was at it. But what I'll probably do instead of, you know, I'll probably put them up on Brightspace, the notes from today. I hope it helped. I think don't underestimate the difficultness of knowing when to use what distribution. Do you know, like, I think sometimes people think, oh, it's it's a lot nicer at the beginning than, let's say, the likes of engineering maths 3 now. But it gets kind of, you know, there's still a lot of tricky stuff in it, and the questions will be cleverly put. I can tell you that. They're always fairly cleverly put. Okay, now some of them are absolutely standard, and all the formulas are given to you. And if you practice, you know, I think you'll do flying. But don't underestimate, read it very carefully and make sure you're picking the right distribution. Again, the more you kind of practice that, you know, you'll get better at that. Are there usually more past exams released? Yeah, you should be able to find, you know, on SharePoint, past exam papers for maths and stats, MA 4004. There should be some past exam papers there. And what I'll do is, you know, in week 13 again, I'll finish the bits of the 2019 that we don't get done because you haven't covered yet, and I'll pick another year and do some questions from that one. So that'll give you another run through, you know, of some questions in week 13, you know, before the final exam. You're very welcome. I hope it helped. And I don't know, if you want to just kind of write down, did you think I went too fast or slow, that I'll try and adapt it for the next time round. You're very welcome, guys. Yeah. And anyone that wants to just, you know, put in, look, maybe speed up a small bit the next time, or slow down, or it was fine, feel free to tell me that as well, or you can email me after. Perfect. All right, perfect. Yeah, no, that's handy for me to know, you know, because I just kind of, and don't ever shy away from telling me these things, because you know, this is for you guys.